Welcome, curious minds, to a world of knowledge and discovery. We're thrilled to present to you our video dedicated to N-heterocyclic silylene. Enjoy! An N-heterocyclic silylene is an uncharged heterocyclic chemical compound consisting of a divalent silicon atom bonded to two nitrogen atoms. The isolation of the first stable C, also the first stable dicoordinate silicon compound, was reported in 1994 by Michael Denk and Robert West 3 years after Anthony Arduengo first isolated an N-heterocyclic carbene, the lighter congener of Ns. Since their first isolation, Ns have been synthesized and studied with both saturated and unsaturated central rings ranging in size from 4 to 6 atoms. The stability of Ns, especially aromatic unsaturated 5-membered examples, make them useful systems to study the structure and reactivity of silylenes and low-valent main group elements in general. Though not used outside of academic settings, complexes containing Ns are known to be competent catalysts for industrially important reactions. This article focuses on the properties and reactivity of 5-membered Ns. With the groundwork laid, let's now examine synthesis and stability and its connections to our previous discussions. 5-membered N-heterocyclic silylenes are synthesized from 2 carbon diamine or diamine precursors. Reaction with metallic lithium yields a lithiate diamide or diamine that, when stirred with tetravalent sickle, yields a tetravalent dichlorosilicosicle. The compound then is reduced with an alkali metal or potassium graphite to reveal a divalent silicon center. Care must be taken to not over-reduce the silicon. Often triethylamine is added to prevent over-reduction. The yield for this reduction can be as high as 80%. N-heterocyclic silylenes containing silicon with 4-membered rings 1 carbon and 6-membered rings 3 carbons are well known and derived from the reactions of 6 with imidinate and natnet ligands respectively. The silylenes synthesized prior to West and Denk's first Nc decomposed at temperatures below Czech. Alternatively, the original West Nc is exceptionally stable even after heating for 4 months at 150 C dissolved in toluene in a sealed NMR tube. It is also unreactive with Lewis bases and trethylsilane as silylene scavengers, but it does react with air and water C below and decomposes at its melting point 220 C. On the other hand, the saturated Nc with no backbone substitutions is far more reactive as a Lewis acid and far less stable, decomposing at 25 C. In the upcoming section, we'll be shining a light on structure. 5-membered Ns can be classified by the bonding in the 2-carbon backbone of their rings. Saturated Ns have 2 methylene units, the unsaturated have doubly bonded methine carbons, and the benzo-fused Ns share their carbon backbone with a fused aromatic ring. Though other North substituents such as aryl groups are also well known, in general, studies are conducted with tert-butyl groups bonded the nitrogen of the saturated and unsaturated Ns, while the benzo-fused have neopentyl groups. X-ray crystallography and electron diffraction show significant differences between the saturated and unsaturated structures. The NCN angle for the saturated tert-butyl substituted Nc is slightly puckering symmetric ring. The NCN angle of the unsaturated analog is gas phase XRD achieving a planar C-IV ring. Upon saturation of the carbon backbone, the NC bonds shorten from up to up, shorter distances than would be expected for a single bond between nitrogen and divalent silicon. The longer bond in the unsaturated molecule is due to the nitrogen's lone pair electrons delocalization through the carbon bond, resulting in lower Lewis basicity of the nitrogen lone pairs toward the silicon, weakening and lengthening the NC bond. The overall silylene character is supported by strong downfield shifting in RC and MR at up for the unsaturated at up for the Ns compared to their tetravalent dichloride starting materials which resonate at up. Let's now venture into the realm of aromaticity and explore the fascinating intricacies it holds. The structural differences, distinct reactivity, and increased stability of the unsaturated ring is attributed to the olefinic bond which creates an aromatic ring with the 2 nitrogen lone pairs. The C-N bond length discrepancy mentioned above is a strong indication of delocalization. In proton NMR, the vinylic protons resonate at alpha versus alpha for the tetravalent dichloride starting material or alpha for the tetravalent C dihydride. In the tetravalent species, the lack of the silicon's empty ep orbital breaks the ring, causing an uphill shift as the deshielding due to aromatic ring current is lost. Additionally, there are significant discrepancies in the Raman spectroscopy signals between the unsaturated N and tetravalent silicon nanolids, such as Cetal and Spiro. The 4 coordinate silylenes exhibit stretches at 1620 km. Conversely, S resonance is found bifurcated at 1566 km and 1573 km at a much greater intensity. In the divalent species, electron density is shifted out of the K bond into the ring and empty C-ip orbital, weakening the K bond and causing the observed energy drop and shape change in the K resonance. Several computational studies suggest aromatic delocalization over the unsaturated C rings. DFT calculations of C-phosphoryl radical adducts show far greater radical electron delocalization over the rings of unsaturated cis 14% C, 65% ring than the saturated C 58% C, 19% ring. Aromaticity is further supported by calculated heats of hydrogenation. At the AUG level, hydrogenation at the carbon backbone of an unsaturated divalent silicon C is 13 xmol more exothermic than the corresponding hydrogenation of the tetracoordinate silane analog. The stabilization of the divalent silicon ring with an empty ip orbital and in-ring lone pair versus the tetravalent silane which lacks an empty C-ip orbital indicates significant electronic communication between the silicon and the olefinic carbons. Additionally, calculations of nuclear-independent chemical shift of the ring-centered NMR resonances of C at atom indicate a high degree of delocalization about the unsaturated C ring. In reference to the perfectly aromatic cyclopentadienyl anions shift at atom, NHSis data supports the aromaticity of NHSis. In the upcoming section, we'll be dissecting electronics and exploring its implications in greater detail. Computational studies and photoelectron spectroscopy create a more nuanced picture of electronic structure and electron sharing in NHSis. Relevant bonding orbitals in unsaturated 5-membered NHSis can be understood as the molecular orbital mixing of the diamine backbones butadiene-like pi orbitals and the Z and IP orbitals of C. Photoelectron spectra of the unsaturated show a HOMO with 3 peaks at IV, and IV, assign the in-phase overlap of the C-IP-Y orbital and buta-13-diene-like of the diamine. The HOMO in the tetravalent C hydrogenated analog lacks a vacant C-IP-Y orbital and the energy of the is destabilized to -6.56 eV, supporting charge donation from north to C in the silylene. The HOMO1 is the in-plane C lone pair involved in donation. No difference is calculated between the HOMO2 for the unsaturated silylene compared to the corresponding orbital of the silane analog. The original 1994 Denk et al. Photoelectron spectroscopy communication relates this orbital to the diamine orbital, however a 1996 paper from Blakeman et al. Designates this as the nitrogen lone pairs. Either way, both orbital assignments are symmetrically forbidden from overlapping with any C orbital. The HOMO2 does not change in energy upon hydrogenation at C, indicating that much of the overall electronics are unchanged by hydrogenation and underscoring the effects of north to C electron donation in the HOMO and HOMO3. Calculations in the former study at the 6 AUG level showed increased energy level spacing for NH model compounds instead of N-2, but with the same order and proportional spacing. The Blakeman study compared the benzofused C to the ethylene-like unsaturated C, and found by PES that the HOMO is lower by EV and the C lone pair by EV in the benzofused C, suggesting the electron withdrawing power of the phenylene ring makes the benzofused C less nucleophilic. The above tables show orbitals, labeled above by occupation and grouped horizontally based on symmetry orbital parentage. They are reproductions of calculations performed in Denk, Green et al. And Blakeman et al. Experimental energies are from PES of original Westinghouse-like tert-butylensis. Calculated energies are from N-hydride-like C shown in MO graphic. LUMO energies and symmetries were not provided. Natural bond orbital analysis of C provides strong theoretical evidence of electron delocalization. NBO calculations indicate a population of 0.54 electrons in the formerly vacant CEPY orbital. 1.2 electrons would be expected in a pure 6-electron 5-atom ring. The saturated silylene has lower electron delocalization over the heterocyclic NCN system with only 0.33 electrons on C versus 1.33 for perfect 4 electrons shared among 3 atoms. No difference in charge sharing is seen in the bond interaction between C and north of each C. This is also the case with NS. In spite of identical CN bonding, the unsaturated silylene has a lower charge separation in its CN bond than the saturated analog. For the unsaturated analog, C has a charge of 0.87 and each north -1, while the saturated has a charge of 1.05 on C and -1.12 on north. These data show that the stabilization and bond difference between the backbone types is entirely due to interactions. For comparison, in an analogous way, germalenes have a charge near 1 at the germanium while carbenes have close to no net charge on the carbenic carbon. Calculations show, upon coordination to group 11 metal halides e.g. C couple CEPY density, NC bond density, and C atom charge all increase. The change is the result of cis sigma donation to the metal, which causes the CEP orbital to draw electron density from the ring. In this manuscript they calculate Kuckel and Agelbach donation to C to be about 4.5 weaker than the interaction. Interestingly, for all 3 group 11 metals, then C in question is a better donor and acceptor than its germylene and carbene analogues. Atoms in molecules bond energy at critical point calculations show that the north to C bonds in NC are significantly ionic, unlike the highly covalent NC bond in an NHSi. Furthermore, the charge density and the Laplacian at the bond critical points between the silylene and carbene are dissimilar. Silylenes have much lower charge density between C and N, with a positive Laplacian from C to north indicating a more ionic interaction, while the Laplacian is negative going from carbon to nitrogen in an NHC indicating a more covalent bond. Upon coordination to a group 11 metal, the covalent character in the C or Celsius to metal bond is small, but not insignificant, again with a higher covalent character in the carbenic system. Similarly, silicon has a higher Laplacian between it and the group 11 metals than does carbon, indicating a less covalent metal interaction in silylenes as compared to carbons. With the foundation laid, let's embark on a journey into main group reactivity. N-heterocyclic silylenes react with a wide variety of main group compounds, generally adding across unsaturated bonds or inserting into single bonds to yield tetravalent N-heterocyclic silylenes. Brace yourselves for the next chapter, where we'll be dissecting tetramerization. In concentrated solutions, the saturated unsubstituted silylene reacts with itself to form a tetramer with a CC double bond. First one C inserts its divalent silicon into another's NC bond, creating a bicyclic molecule with a tetravalent silicon bonded to a divalent silylene. The mixed valent dimer then itself dimerizes, forming a 4-silicon silene with 229 cis double bond. Though exceptionally long, the bond order is supported by Raman spectroscopy. Reacting the tetramer with methanol results in the mixed valent dimer methanol adduct and not the silene dimer adduct see below. Additionally, a double bond between tert-butyl substituted cis is calculated to not be stable, further corroborating the identity of the mixed valent dimer as the intermediate. Unsaturated and backbone substituted saturated cis such as the 45-dimethyl are not reactive in this way and as remain monomers. Similarly, the unsubstituted cis will react with analogous north heterocyclic germalenes, ultimately forming a silicon-flanked german. Get ready to uncover the mysteries surrounding reactions with chalcogens as we navigate its intriguing terrain. Reacting cis with oxygen strips the diamine backbone and produces solid silicon dioxide, likely through a twin-C deoxo-bridged intermediate. Reactions with one equivalent of yields a dithio-bridged twin-C complex. The formation of the dithiodimer occurs through an intermediate attributed to a thiosilylene with a CS double bond. Excess sulfur yields a repeating oligomer with complementary diamine loss. The analogous reaction with selenium is far slower, but yields the diselenium-bridged DNC exclusively. As we progress, let's zoom in on reactions with bonds and examine its role in shaping our overall narrative. Cis insert into bonds to form terminal silane-like products, C disilane bridges, or oxo-bridged C-siloxanes. Alcohols react with C to form exclusively the silyl ether. With water, cis will insert to each of the OH bonds to form a siloxane. A more varied reactivity is seen with halogens. Cis insert directly into the Ci bond of idomethane. Alternatively, when saturated or unsaturated cis are reacted with dichloromethane, chloroform, or carbon tetrachloride, the silicon centers of cis form a bond, with one halide adding to one silicon and the remaining organic fragment adding to the other. Other halocarbons will yield a mixture of mono and disilane products. The resulting mixture of products as well as computational studies indicate that a free radical mechanism brings about these products, with the radical pathway being 16 to 23 xmol lower in energy than concerted mechanisms. Upon heating, the disilenes either disproportionate to N-silane and silylene, or form a one-carbon bridge between two CX fragments in a vein similar to water's reactivity. In the presence of silicon tetrachloride, benzofused cis will insert between two cycle bonds to form a trisilane. With our foundation established, it's time to explore reactions with bonds and its relevance to our overarching theme. Generally, when reacting with unsaturated species, NHSi will add across a double or triple bond to form a spirocyclic compound, containing one or two equivalents of NHSi-derived silicon. Alkenes and alkenes react with cis only if their C-C bond is highly polarized, such as is the case with phenyltrimethylsilylestyrene, which produces a silicocyclopropene with one C equivalent or a disilicocyclobutene with two. With ketones, two equivalents of benzofused C react to form disilylexitones as well as further reaction products depending on the carbon substituents. Dienes, as well as heterodienes, including benzyl or the common C backbone and diethybutyl-diazobutadiene, react in a fashion to yield molecules with two 5-membered rings sharing a single silicon atom. Amines do not form simple cyclic silylene additions. Benzofused cis react with the diamine and orthocarbons of N-tert-butyl-phenylamine to form a 5-membered ring composed of the N-C-silicon, one carbon and nitrogen of the imine and the ipso and paracarbons of the phenyl group, through an intermediate that breaks the phenyl aromaticity. Cis add across neutral CN bonds, first forming a 3-membered ring, subsequently a second C inserts to complete a 4-membered ring, similar to the reactivity of an alkene. Alternatively, tert-butyl isocyanide reacts more like an alkyl halide with a single silicon bonding to the tert-butyl fragment and the carbon of the cyanide groups, or with two cis to form an acyclic BuCCCN product. There is evidence that the single silicon C-nitrile interconverts in small quantities to the silicon S-nitrile. As we enter this new chapter, let's navigate the complexities of azelaic acid and unravel its multifaceted nature. N-heterocyclic silylenes are generally considered to be Lewis bases, though their reactivity can occasionally differ. With the Lewis acid trispentafluorophenylburon, the expected acid-base adduct forms. However, over long periods of time, the silicon will insert between a BC bond, oxidizing the silene to silane. Additionally, in rare cases, NHSi can act as a Lewis acid. Reaction of the n-dinyl besnophystancy with the analogous carbene creates a long, highly polarized C-C bond. The carbene carbon becomes a carbocation, remaining nearly planar, while the pyrimidalized silicon adopts a negative charge. With our curiosity piqued, let's embark on a dedicated exploration of N-heterocyclic silylenes as ligands and its fascinating intricacies. Though with less variety and fewer applications than their lighter analogues, the N-heterocyclic carbenes, N-heterocyclic silylenes are known to act as ligands in a range of metal complexes. Unlike most non-silylenes, which are Lewis acidic, stable 5-membered cis act almost exclusively as a Lewis bases or nucleophiles in a manner similar to Ns and phosphine ligands. Both the saturated and unsaturated 5-membered cis are calculated to have substantial single-triplet energy gaps at 74 xmol and 69 xmol respectively for the hydride N-substituted models. As a result of the large energy gap, electron density is concentrated exclusively in the in-plane donating Z-lone pair, while donation from the ring stabilizes the formerly vacant, slightly accepting CP orbital. Though weak, as discussed above, Cis do exhibit metal to C-it backbonding, as evidenced by the shortness of C metal bonds compared to standard metal C single bonds. In the complex, then C readily takes the place of strongly backbonding carbonyls. For the tridonyl bipyramidal ion, then C adopts an equatorial position over axial, with shorter equatorial phase distance versus due to better overlap of the empty acidic ip orbital with the metal d orbitals at this position. Sterically, cis resemblance, however, the tighter NCN angle C and longer CNC and C metal bond length compared to carbenes NCN angle C, CN bond length C, and C metal length means C are less sterically demanding, leading to reactivity not seen in carbenes. Without further ado, let's move on to the topic of transition metal complexes and reactivity. N-heterocyclic silylenes readily substitute carbonyl, cyclotadene, and phosphine ligands in metal complexes. Additionally, silylenes can react with metals by inserting between metal ligand bonds or by acting as a reducing agent. Conform to distinct molybdenine adducts depending on molybdenum precursor. With the phosphine is replaced, while with NC inserts between a metal hydride bond to form a tetravalent silane ligand. The orbitals of the triphosphine substitution product are unable to form interaction as exhibited by a RCNMR signal of which indicates silicinium C character, while the molybdenum has a resonance at As mentioned above, unsaturated C reacts with FeCO to form both the axial and equatorial frequency. Similarly, the same C reacts with RuCO to form the axially trans disubstituted. Reaction of with creates in high yield. Upon heating, two equivalents of lose a total of 2 asteneutral ligands and 1 C to form a deuterium complex where one RUC unit is coordinated by the C in a fashion, while the other CPRU center is complexed in a fashion by the 6th electron putatively aromatic surface formed by the unsaturated C ring. Nickel reacts with 4 equivalents of benzo-fused C to form an inside, while 5 equivalents are needed to produce the tetraikis C complex. The extra C equivalent is needed to reduce the Ni center, forming 1 equivalent of cycle in the process. Both the saturated and unsaturated 5-membered cis react with, producing a 2-put complex with 2 terminal and 2 bridging cis. This unstable intermediate converts to a more stable complex with bridging silylenes and 2 terminal phosphines. Likewise, starting materials are unable to produce, however, reduction of with 6 equivalents of C produces or can also be produced by reacting coordinated by just 2 N-terbutyls with 3 equivalents of C. 2 factors contribute to this difference. The greater steric bulk of the NHC makes it able to accommodate only 2 ligands, and calculations show that C has a 3.6 xmol stronger bond than the NHC. Beyond being interesting models to study the structure and bonding of low-valent silicon and cis transition metal complexes have been demonstrated as active catalysts in industrially important reactions. The D-silylene bridged palladium phosphine complex, first synthesized in 2001, has palladium in the Zroth oxidation state and is effective at Suzuki coupling. At 5% catalyst loading, the easily synthesized C-bridged complex is able to form a carbon-carbon bond between phenylboric acid and O-bromocytophenin at 88% yield. In another example, Denk synthesized from and was found to be more effective than its NHSi analog at Heck coupling. With 1% catalyst loading at 140 C, the silylene complex catalyzed the coupling of p-bromocytophenin and styrene in 4 hours in quantitative yield. Under the same conditions, the corresponding NHC complex yields only 91% product, showing that there are instances where the electronics or sterics do make silylenes comparatively superior catalysts. Share this video with your friends and spread the knowledge.